My name is Lorna Dawson, and I'm going to talk to you today about soil. When we consider soils, we need to understand the definitions of some words that are commonly used when studying soils. First of all, let us consider what soil is. Soil can be defined as a solid material on the Earth's surface that results from the interaction of weathering and biological activity on the parent material, or sometimes known as the underlying hard rock. The parent material is the material from which soils are formed. It is often, but not always, the underlying hard rock. The study of soils as naturally occurring phenomena is called pedology. It comes from the Greek word pedon, meaning soil or earth. Pedology takes into account the factors and processes of soil formation, soil characteristics, and the distribution of soil types. We will be covering all of these topics later on in this lecture. When considering a soil, we think about the soil profile, which is the basic unit of study. A soil profile is a vertical cross-section of a soil. It is divided into a number of distinct horizontal layers, referred to as horizons. Horizons are the layers in the soil, often distinguished on the basis of differences in colour, hardness, or structure. The horizons are normally designated by symbols and letters, as in this picture of a soil profile. Note the three horizons shown here: a topsoil, the upper or A horizon, a subsoil, middle or B horizon, and at the bottom of the soil profile parent material, the lower or C horizon. This is a very simple soil profile, and often there are many more horizons than this. In addition, the organic or O horizon can form above the mineral soil. This occurs commonly in forested areas and results from the remains of dead plants and animals. As I mentioned in the previous slide, soil horizons are often more complicated, and this soil profile on this slide shows a more complicated series of horizons. The horizons may be further divided. For example, in this soil profile, the A horizon has been divided into 4 further pedological horizons. The first is the dead vegetation, litter, or called the L horizon. This material is on the surface of the soil and is not readily incorporated into the soil, although in time it will be worked into the horizons below, provided there is organisms in the soil to do that. Then the F horizon is below that, which consists of fermenting leaf litter. Below this is the H, or humus horizon. Humus is the well-decomposed organic material which tends to be very dark in colour and has very little structure to it, what we term amorphous. When you examine the factors which are at play in forming a soil profile, it's important to consider the main factors that operate: the climate at that location, the vegetation which is growing there, the range of soil organisms which are living and working there, the drainage in that area, and the relief, and also, as we've heard before, the underlying parent material. We are now going to consider each of these factors of soil formation in turn, but you must remember that each of these factors of soil formation interact with each other. Climate is probably the most important factor. For example, soils produced from the same parent material under different climates can be very different. Climate governs the rate and type of soil formation and is also the main determinant of vegetation distribution. Soil climate has 2 major components: moisture, primarily from precipitation, and temperature, influencing evaporation. When precipitation exceeds evaporation, leaching of the soil will occur. Most chemical or biological reactions need water to be present. But temperature determines the rate of reactions such as chemical and biological decay, and so has an influence on weathering and humification. That is, the breakdown of organic matter into its component parts. If we first consider parent material, it is the material from which the soil has developed, and it can vary from solid rock, such as a granite, to looser deposits like alluvium and boulder clay. It has been defined as the initial state of the soil system by the great Swiss soil scientist Hans Jenny in 1941. The parent material weathers over time and has a large effect on any soil we consider today, as it influences soil colour, soil texture, soil structure, the mineral composition of the soil, and the soil's permeability or ability to drain. Soil texture refers to the distribution of particle sizes within the mineral component of the soil and will be covered in more detail later. The soil structure refers to the arrangement of the soil particles. Basically, it's the soil's architecture. This soil in the picture has developed on an old red sandstone and so has derived its distinctive red colour from its parent material. It is also likely to be a sandy textured soil due to characteristics of its parent material. Higher plants, the vegetation, influence the soil in many ways. The nature of the soil humus is determined by the vegetation cover and the resultant litter inputs from that vegetation. For example, compare the acidic litter that comes from coniferous Sitka spruce needles with the more nutrient-rich litter from deciduous beech leaves. Roots contribute dead roots also to the soil. They bind the soil particles together and can redistribute and compress soil as well, and can remove nutrients from the soil. The roots also help aerate and assist the soil drainage, as deeper roots penetrate deeper down into the soil. When we use the term organisms, we include vegetation or flora, animals, the fauna, soil microorganisms such as bacteria and fungi, and also man, who in some instances has had a huge impact on soil formation. Organisms influencing soil development range from microscopic bacteria to large animals, including man. Microorganisms such as bacteria and fungi assist in the decomposition of the plant litter. This litter is mixed into the soil by macroorganisms, the soil animals, such as earthworms and beetles. Soil horizons are less distinct when there is much less organism activity. Higher plants influence the soil in many ways. The nature of the soil humus is determined by the vegetation cover and the resultant litter inputs. Roots contribute dead roots to the soil and can redistribute and compress soil. The drawing above shows living organisms in the soil beneath a deciduous woodland. The circles of increasing magnification show soil animals, fungi, and microorganisms. Springtails, which are also known as collembola, occur in large numbers in leaf litter. Ectomycorrhizal root tips occur in woodland. Ectomycorrhizae are a symbiotic relationship between a fungi and a root. In ectomycorrhizae, the fungus sheathes the root tip. At a higher magnification, you can see a root tip covered in fungus, which is, in turn, covered with bacteria. And finally, you can see images of the tiny soil bacteria. It must always be remembered that from a spoonful of soil, millions of bacteria and other microorganisms can be isolated. and there are more microorganisms in a teaspoonful of soil than there are people living on this planet. Relief is another factor of soil formation and encompasses landforms and topography. But relief is not static, it is a very dynamic system. Its study is called geomorphology, and the relief influences soil formation in several ways. Firstly, it influences soil profile thickness. As an angle of slope increases, so does the erosion hazard. Soils developing on flat ground will tend therefore to be deeper than soils developing on sloping ground. Relief has an effect on climate, which is also a soil forming factor. For example, as altitude increases, the air temperature decreases. The gradient of land affects runoff, percolation and mass movement. Relief influences aspect, which also creates microclimatic conditions. And in the northern hemisphere, a south-facing slope will tend to be warmer than a north-facing slope. In this photograph, soils are thin on the glacial eroded rock outcrops, but are much deeper on the flat, raised beach deposits in the foreground. Drainage is very important for affecting many of the soil characteristics that we see. The blue-grey colour of glaze indicate poor drainage. If the water permeates a clay soil all year round, it is called a groundwater clay. If only the surface is poorly drained, mainly in spring meltwater areas, the soil is called a surface water clay. A peaty clay soil is waterlogged for most of the year. This waterlogging denies the soil the oxygen that the soil organisms need to survive. Consequently, they are poorly drained. The soil organisms extract the oxygen they need to survive from the iron compounds, and the soil gradually turns grey, blue or green as the oxygen is depleted. These mottles are indicators of poor drainage. Soils are very complex and dynamic systems in which many processes are taking place. The processes we are going to consider in the next few slides are weathering, decomposition, humification, leaching, and capillary action. Weathering refers to the breakdown and decomposition of rocks and minerals by factors including air, water, sun and frost. Physical weathering involves continual breakdown of rocks into smaller and smaller particles, often as a result of temperature changes. Chemical weathering involves alteration of the chemical composition of the rock minerals, and freeze-thaw weathering is a good example of physical weathering. Decomposition is the overall term for breakdown of plant-derived material into its simpler organic constituents. This is accomplished by enzymes, earthworms, mites, and other organisms. Humification is specifically the breakdown of plant remains, which leads to the formation of different types of humus. It is probably the most important biological process taking place in soils. Mull humus develops under deciduous woodland, where base-rich plant remains are actively broken down by prolific soil biota, while the moor humus develops beneath coniferous woodland or heather moorland under cool, wet climatic conditions. Breakdown here is slow, and there is an absence of many soil biota. Where evaporation exceeds precipitation in a soil profile, moisture moves upwards within that soil profile by capillary action. It is the reverse direction to leaching. In Britain, precipitation generally exceeds evaporation, and as a result, capillary action in British soils rarely occurs, apart from in very sandy soils at times of very low rainfall. Wherever rainfall exceeds evaporation and there is free downward movement of water through the soil pore system, soluble minerals are moved downwards or even leached from the soil profile in a process known as leaching. Continual leaching tends to impoverish the upper mineral horizons by removing the basic cations. Cations are ions having a positive electrical charge, for example, the calcium ion. The leaching is most active in sandy soils where there is a high porosity, and is least in fine textured soils such as clays, which have restricted pore spaces and which can hold on to cations due to negative charges at the edge of the clay minerals. The diagram above shows a soil with small peds or crumbs with a high porosity, which leads to free drainage and active leaching down the soil profile. The upper mineral horizon, losing the material in this photo above, is the alluvial or E horizon. This is where maximum leaching or alluviation, from the Latin word ex or E meaning out and lux meaning washed, takes place. The E horizon, shown near the surface of the podzol in this picture, is a good example of an alluvial horizon. The lower horizon gaining the material is the alluvial horizon and is often a subsoil or a B horizon. This is from the Latin words ill, meaning in, and love, meaning washed. This is the zone of maximum accumulation as it is gaining the material from the upper horizon. Generally, the soil colour is determined by the amount of organic matter in the soil and also the state of the iron. Soil colour is also related in part to soil drainage, with free draining, well aerated soils, that is, soils where the pore space is dominated by oxygen, rather than water having rich brown colours. In contrast, poorly drained soils, often referred to as glaze, develop under anaerobic conditions. This is where pore space is dominated by water and there is little oxygen present, and they have a grey or a blue-grey colour. Soils with periodic waterlogging are imperfectly drained soils and are often highly mottled with blotches of colour different from the predominant soil colour. Mottles are often rusty in colour and are due to iron concentration patches. This can be seen in the lower picture on the slide. Soil texture is a term used to describe the distribution of the different sizes of mineral particles in a soil. It refers only to the mineral material which is less than 2 millimeters in size. Textures range from clay, that's material smaller than 0.002 millimeters. Sand, the material which is between 0.06 and 2 millimeters in size, and silt, the middle-sized particles which are sized between 0.002 and 0.06 millimeters. To a loam, which has all three size fractions present. In fact, the majority of soils have a mixture of all particle sizes. The main influence of texture is on soil permeability, which generally decreases with decreasing particle size. The picture on the right shows two soils. The soil clod on the right is dense with a poor texture and leads to a poor structure if badly managed. Due to continual compaction, it is blue-grey in colour due to low oxygen conditions. It is therefore a poor environment for root development, whereas the soil clod on the left has been well managed and is relatively loose with ample pore space for good, healthy root development. The picture on the left shows a soil which is high in silt and clay and which has a compact subsoil, leading to compaction in pore spaces. It would be difficult for roots to penetrate into this subsoil. Now you can test yourselves. Questions such as, What factors might contribute to the visible differences between these two different soils? The answer is all factors of soil formation will lead to differences between these two soils. The climate at the location, with likely drier and warmer at the one on the left compared with the wetter and colder conditions for the one on the right. The vegetation, which can affect the acidity of the decomposing litter. The soil organisms, which are living and working in the left-hand profile, and it'll mix the profile by being active, while on the right-hand side fewer earthworms will be active. The soil on the left-hand side will have better drainage than the one on the right-hand side, more aeration on the one on the left-hand side and more waterlogging in the right-hand side soil profile. And relief, with the right-hand profile being more likely located in a depression in the landscape. And of course, the underlying parent material will contribute colours and texture to the soil by the minerals present in the bedrock. In question number 2, what type of humus is most likely to develop in this environment? Answer. This is an upland environment with a pine woodland, with heather moorland in the foreground, creating acidic litter which falls onto the soil, forming an acidic moor type humus. Question 3. How do soil biota, such as earthworms above, assist in the formation of soils? Answer. Earthworms are active in brown earth soils as they move through the soil horizons, mixing up the soil horizons and helping create better drainage in soils. The earthworm is sometimes called our ecosystem engineer. Question 4. What indicates that the lower part of this soil is poorly drained and lacks aeration? Answer. The grey colour and the orange-brown mottles and the fine texture. Question 5. What process is producing this layer in the soil? Answer. Decomposition. Decomposition is the breakdown of plant-derived material into its simpler organic constituents. It is through the action of enzymes, earthworms, mites and other organisms, and humification, which is the breakdown of plant remains, which leads to the formation of the different types of humus. It's probably the most important biological process taking place in soils. Question 6. What is a vertical cross-section through a soil called? Answer. Soil profile. Question. What name is given to the layers in a soil cross-section? Answer. Soil horizon. Question 7. Explain how the relief shown in this photograph may affect soil formation. Answer. Relief affects soil profile thickness. For example, as an angle of slope increases, so does the erosion hazard and therefore the risk of soil loss. It also has an effect on climate, which is also a soil forming factor. Gradient affects runoff, percolation and mass movement, so the steep slopes are likely to be shallow, while the lower flat areas will likely be deeper. Relief influences aspect, which creates microclimatic conditions, with south-facing slopes having much faster decomposition as they are much warmer. Question 8. Why is leaching of the soil likely to be occurring in this part of northwest Scotland? Answer. Because here precipitation exceeds evaporation and the water runs through the soil profile and leaches the nutrients out. Question 9. Which layer in this soil is alluviated? Answer. The grey bleached horizon where iron and aluminium have been leached out from. Question. Which layer in this soil is illuviated? Answer. It's the dark horizon where the iron and aluminium have been deposited. As you will see now, as a result of the many different factors affecting soil formation and the many different processes going on in our soils, there are so many different soil types as a result. The soils in Scotland are diverse, and they're found in varying amounts in different parts of the country. Look at where the brown earths, podzols and clay soils are found. Most brown earths are found in the low-lying lands of the east coast of Scotland, while the glays are located in the central belt of Scotland, and many of the podzols are located in hilly terrain. Soils play an essential part in all our lives, providing us with a wide range of benefits. Some of these benefits are obvious, like growing food for us to eat, while many are less clear, like filtering the water for us to drink, reducing a flood risk, and influencing climate change. You can explore more by looking at Scotland's Environment Web. Thank you for taking the time to learn about soils in the environment and soils in Scotland.